Hello, and welcome to Linear Algebra. This is lecture 23, and our topic is inner products. Last time, we talked about triangularization. The theme was trying to find the best representative for a linear map, so the best matrix associated to a given linear map. And one answer, whenever you're working over an algebraically closed field, is an upper triangular matrix. I mentioned that in some sense, the best answer would be a diagonal matrix, but that although we know exactly when a matrix is diagonalizable, namely when it has there is a basis of the space consisting entirely of eigenvectors, that is perhaps a criterion that's hard to check. There is a simpler criterion that occurs sometimes, and that is in the context of inner product spaces. So we're going to start studying those today. So this time specifically inner products, and inner products are generalizations of the dot product. So an inner product is a product of vectors that gives you back an element to the field, generalizing the dot product that we're used to on our end. So from now on, we'll assume that the field we're working on is either the real numbers or the complex numbers. Okay, for most of the rest of the semester, we'll have this assumption. When we get to determinants, we'll allow the field to be arbitrary again. But until then, we're going to assume that the field is either the real numbers or the complex numbers. So let me remind you from the complex numbers. That if you write a complex number as a plus ib with a and b real numbers, right, then a is known as the real part of z, we'll denote it re of z, and b is known as the imaginary part of z, we'll denote it im of z. Notice that the imaginary part of a complex number is a real number, right? It's the coefficient of I. And then the complex modulus is the square root of a squared plus b squared. Also, the complex conjugate is a minus ib, and a very useful formula for the modulus squared is you can take just complex multiplication, z bar times z. This gives you a real number. In fact, that real number is the modulus of z squared, a squared plus b squared. Okay. So here's the definition. If V is a vector space over F, here F is either R or C, then an inner product on V is an operation denoted with triangular brackets such that, okay, first of all, it's scalar valued. Right, so the inner product of two vectors is an element of the field for any two vectors in the vector space. Secondly, it is linear in the first entry. So for any vectors u, v, w in the vector space and any scalar c in the field, the inner product of u plus cv with w is equal to the inner product of u with w plus c times the inner product of v and w. Okay. It is conjugate symmetric. Right? So it has conjugate symmetry, which means that for any VW in the vector space, the inner product of VW is equal to the complex conjugate of the inner product of W with V, right? So the order matters. If you change the order, you get complex conjugate. Now, of course, if you're working with the real numbers, a real number is equal to its complex conjugate. So this says that for real numbers, the inner product is symmetric. But for complex numbers, it's not. Fourth property is that it is non-negative, right? So this says for any vector, the inner product of a vector with itself is a real number and non-negative. And finally, the inner product is definite. Right? So what definite means is that if you take a vector inner product with itself and you get 0, then the vector itself was 0. Okay, so that's the definition. The second one talks about being linear in the first entry. So you could ask, well, what happens with the second entry? Well, that's determined by properties 2 and 3. So combining properties 2 and 3, we see that the inner product is almost linear in its second entry. So what happens in the second entry? Well, let's say you pick 3 vectors, u, v, w, inside the vector space, and then a scalar, say f. And so let's take a linear combination in the second entry. Right? Well, what we could do is we can flip the order of the vectors in the inner product, but we pay for it with a complex conjugate. Now, in the first entry, we know that the inner product is linear. So I can write this as the inner product of v with u plus c times the inner product of w with u. But again, I'm paying with a complex conjugate. Now, the complex conjugate of a sum is equal to the sum of the complex conjugate. The inner complex conjugate of a product is equal to the product of the complex conjugates. So I can write this as the inner product of v and u complex conjugate plus c complex conjugate inner product of w and u complex conjugate. And now I can use this conjugate symmetry again to flip the order here plus c bar with the order here. Okay, so notice we started with this and we ended up with this. So it's almost what you would get if you were to have something linear in the second entry, except that the c gets pulled out as a c bar, right? So we say it's conjugate linear because the scalars get pulled out with a conjugate. Okay, so examples. So there's the dot product. So our motivating example was the dot product on Rn. So if U is the vector with entries U1 through Un, V is the vector with entries V1 through Vn, then the inner product of U and V, which is usually denoted U dot V, is equal to the sum, j goes from 1 to n, of uj times vj, right? And in vector notation, we can write that as u transpose times v, right? So if we think of a vector as being a matrix, in this case of size n by 1, then u transpose times v is a 1 by 1 matrix, and it is just the dot product of the two vectors. We used this when we were talking about matrix multiplication, or even matrix vector multiplication. Right. Notice that this is a real inner product, so it is symmetric. The product of u transpose with v is the same as the product of v transpose with u. Okay, so that's the dot product on Rn. We'll also call it the standard inner product on Rn. The complex numbers have one too. We will call the standard inner product on Cn. So here, very similar. Let's use different letters. Let's say that W is the vector with entries W1 through Wn. These are n complex numbers. And let's say that Z is the vector with entries C1 through Cn, n complex numbers. Then the inner product is the sum, j goes from 1 to n, of wj cj bar. Right, so you put a bar on the entries of the second vector. Right, this makes sense because we want the second entry to be conjugate linear. So that's arranged by putting a conjugate on the second entry. Notice that if you just had a vector and itself, so zz bar, and let's say that n was equal to 1, so you just have a single complex number, then what you're getting here for the standard inner product of z with itself is c times c conjugate. And that makes a lot of sense, because if we go back to the beginning, c times c conjugate is how you get the modulus squared. Okay, we can also write this in terms of matrix multiplication when we consider W and Z as n by 1 matrices. But in this case, instead of using the transpose, you want to use the adjoint. Right, so this is denoted with an asterisk instead of a T. So in this case, this would be C star W, where these are vectors. Okay, so I hope it will not be confusing that we are using in the lecture videos bar to denote vectors and also bar to denote complex conjugates. So hopefully it'll be clear that this just means the vector z, whereas here I mean the complex conjugate of the entry zj. In the notes on the course website, I use colors to denote the vectors, so that hopefully will be clearer. And if you download those first and follow along there, then there shouldn't be any confusion about what is a vector and what is not a vector. Okay, but in any case, that's the standard inner product. And notice that this one is not symmetric, because if I were to put them in the opposite order, then the ones they get conjugated are different. Here's a third example. So let's say that you're working on the continuous functions on 0, 1 with entries, values in the complex numbers. So f from 0, 1 to complex numbers such that f is continuous. So here's an inner product on these functions. You integrate from 0 to 1 f of x against g of x bar dx. So notice that this is very similar to the standard inner product on Cn. It's just that we replace the sum with an integral. Okay. Here's a simple remark. For any v in the vector space, the inner product of the 0 vector with v, well, that's the same as the inner product of v against the 0 vector. That is always the scalar 0, no matter what v you're using. And 0 is the only vector with this property. So it's the only vector for which the inner product is always equal to 0. So that's easy to see, because if w were a vector such that the inner product of v with w were equal to 0 for all v, then, well, then in particular, the inner product of w with w would be 0. So by the definition of inner product, w has to be 0. Okay, so 0 is the only vector against which you always get 0 inner product. Right, why is it called the inner product? Well, the name comes from Grassmann, Hermann Grassmann, who, as I've mentioned in one of the historical asides at the end of a class, his book was famously difficult to read. So it's not entirely clear why he called it an inner product. There are a couple of theories. One of them is that it's from this expression, that the t goes in between the two vectors. So it's in the two vectors, and that's why it's inner. There's a second theory that I like better about why he called it an inner product that I'll mention at the end of class. Okay, so definition. The norm of a vector be in an inner product space. Right, an inner product space is a vector space with an inner product. Is, so norm of v, so the notation is like absolute value, but we would put 2 bars instead of just 1. And what it is the square root of the inner product of v with itself. Right. So notice that this makes sense because we required in the definition of an inner product that the inner product of a vector with itself is a positive real number. Well, a non-negative real number, and you get 0 if and only if you have the 0 vector. A unit vector is what we call a vector of norm 1. Okay, so let's compute an example. So consider a function continuous with complex values on the interval, the unit interval, given by f of x equals 2x plus 3i. Okay, then the norm of f squared is by definition the inner product of f with itself. right? If we're using the inner product from the previous set of examples, then this is the integral from 0 to 1 of f of x against f of x bar dx, which is the same as saying the modulus of f of x squared. And in this case, that would mean the modulus of 2x plus 3i squared x. Right now, the modulus is the real part squared plus the imaginary part squared. And if you do this integral, you get 4/3 plus 9. So that means that the norm of f is the square root of this. So this would be the square root of 31 divided by 3. Okay. Here's a simple observation. Let's make it a remark. The norm is positive homogeneous. Right? So the norm is definitely not a linear map, but it is positive homogeneous. So what that means, so remember homogeneous we saw when we talked about linear maps. Homogeneous meant that multiplication by a scalar was this, you gave the same answer whether you did it before you applied the linear map or after you applied the linear map. The norm is positive homogeneous, so what that means here is that for any vector B and C in the field, the norm of C times V, right? Okay, well, by definition, that is the square root of the inner product of C times V with C times V. Now, because the inner product is linear in the first entry, I can pull out a C from the first entry. And because it is conjugate linear in the second entry, I can pull out a C bar from the second entry. And then C times C bar, well, C is just a scalar, so that's just modulus of C squared. And then I can pull that out as the square root, and I end up with modulus C times the square root of the inner product of V with itself, and that is the absolute value of C, or the modulus of C, times the norm of V. So when you multiply a vector with a scalar and then take the norm, what you get is the norm of the vector scaled by the modulus of the scalar, right? So in particular, if C is a positive number, then you just pull the C out, right? So we say it's positive homogeneous. Okay. Just like when we have the inner product, we can use an, just like when we have the dot product, we can use an inner product to talk about when vectors are orthogonal to each other. So we'll say the two vectors, V and W, are orthogonal or perpendicular which we'll often abbreviate by putting this perp sign between them, if the inner product of V and W is equal to 0. A list of vectors, or a set of vectors, V1 through Vn in V is called orthogonal if the inner product of Vj and Vk is equal to 0 whenever j is different from k. Okay, and If you have an orthogonal list of vectors and all of those vectors have unit length, then you say that it is orthonormal. Okay, so orthogonal vectors, just like your geometric intuition would tell you, are linearly independent. Let me put that as a theorem. An orthogonal list of vectors of non-zero vectors. Right, so the zero vector, another way of saying what we saw before, is that the zero vector is orthogonal to all vectors. So let's say you have an orthogonal list of non-zero vectors, then it is linearly independent. Okay, so let's prove this. So, well, to prove it, let's start by just giving things names. Suppose the list is V1 through Vn. Okay, every proof of linear independence starts the same way. You have some vectors, you want to show they're linearly independent. You start by assuming that you have a linear combination equal to 0, and then you need to show that the coefficients are 0. Okay, every proof of linear independence starts the same way. So it's a proof of linear independence, so that's how we start. Assume that a1 v1 plus dot 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 an vn is equal to 0 for some a1 through an in the field. We want to show that aj is equal to 0 for every j. Okay, so we take a linear combination equal to 0. We want to show that it has to be the trivial linear combination. Okay, and in this case, it turns out we can show that the coefficients are 0 one at a time. So, we have this vector, and we're studying inner product spaces, so we clearly should take the inner product of this vector with somebody. So let's say for any VL in this list, let's take the inner product of this linear combination with VL. Right? So on the one hand, we know that this is equal to 0, right? Because this linear combination is the vector 0, and we know that the inner product of 0 with any vector is 0. So on the one hand, we know this inner product is 0. On the other hand, because the inner product is linear in the first entry, we know that this is equal to a1 times the inner product of v1 with vl plus dot 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 an times the inner product of vn with vl. Okay, now because it's an orthogonal list, I know that all of these inner products are 0, except for the one where I have VL inner product with itself. So because it's an orthogonal list, I know that this is equal just to AL times the inner product of VL with VL. Now, because all of these vectors are non-zero, I know that inner product of VL with itself is not 0. Now, if the product of this number and this number is equal to 0, then I conclude that AL is equal to 0. Right? So since VL is not equal to 0, so the inner product of VL with VL, which incidentally is the norm of VL squared, this is not 0, then AL must be 0. And since this was true for any VL, we're done. We've shown that all of the coefficients have to be 0. Okay, great. So our geometric intuition works there. orthogonal vectors are linearly independent. Here's another fact we're used to that is still true in this more general context. The Pythagorean theorem. So if V1 through Vk is an orthogonal list, then the norm of the sum of these vectors squared is equal to the sum of the norms squared. Okay, so why is this the Pythagorean theorem? Well, remember how to do the sum. So if I had just two vectors, v and w, sorry, that's not w, v and something orthogonal to it, w, right? Then the way I do the sum is I would put the w over here, and then I would draw the vector joining the endpoints. And here, so let me go ahead and label this guy as w. So then this vector is v plus w, and this angle is 90 degrees. So in the case of two vectors, you see that this is the classical Pythagorean theorem setup. And the Pythagorean theorem tells us that the length of this vector squared is equal to the sum of the lengths of this vector squared and this vector squared. And that's exactly what we're saying is true in any inner product space. Okay, so the proof is straightforward. We'll just start with the left-hand side and work our way to the right-hand side. So the norm of the sum of the VJs squared is equal, by definition, to the inner product of the sum of the VJs with itself. Here, let's use a separate variable here. Let's use L, that's from 1 to K, L. Okay, and now because this is linear in the first entry and almost linear in the second entry, I can pull out the sums. And I just get a big sum, a double sum, of the inner products of VJs with the VLs, right? But now, these vanish. So for each J, I have a sum over L. And all of these terms vanish except for the one where L is equal to J. So this is equal to the sum J goes from 1 to K, the inner product of VJ with VJ. Right? But we're done because that's the sum J goes from 1 to K of the norm of VJ squared. That's what we wanted to show. Okay. So finally, let's finish with a lemma. So this lemma says, given U, well, let's start with V and W in a vector space with an inner product. We can find a vector U orthogonal to W, such that V is equal to AW plus U. Okay, so you give me any two vectors, then I can write one of those as a multiple of the other one plus something orthogonal to it. In fact, if W is not equal to 0, so if W is not the 0 vector, W is the 0 vector, this is a really simple lemma. But if W is not equal to 0, we can take A to be this number. So take the inner product of V and W and divide it by the norm of W squared. And we can take U to be V minus this number times W. Okay, so let me draw a picture. What this says is that if you have a vector V and a vector W, let's say this is V, this is W, then the theorem, the lemma says that, oh, well, if you were to scale W so that you get A times W, then the difference between where you land and V gives you a vector, so this would be U, orthogonal to W, right? So you can see that what we're doing is projecting the vector V onto the line spanned by W. So we're getting a multiple of W, right? So it's this projection. And this brings me to the other reason given for why Grassmann called it an inner product, right? So you see A is basically the inner product depending on the size of W. But if W were a unit vector, A would just be the inner product. And A is how much you're multiplying. So the inner product for when you have a unit vector, when W is a unit vector, is just telling you the projection. How big is the projection of V onto the line spanned by W? So the idea is that it's the inner product because it's telling you how much of V is in W, right? Hence inner product. So who knows? Maybe I like that story of why it's called that. Okay, so let's prove this. So the proof is really easy in that I've already written down who A and U are, right? So the theorem says that if you start with V and W, then you can write V like that. You can find A and U so that you can write V like that. Well, I've already told you if W is equal to 0, I don't have anything to prove. If W is not equal to 0, then I've already told you who A and U are, and it's definitely true. So suppose W is not equal to 0. So clearly, V is equal to A times W plus U with A and U as above. So we just need to check that this U that I wrote down is orthogonal to W. Okay, so if we check that, then we're done. And indeed. So to check if these are orthogonal, I need to take the inner product of U and W, and I need to get 0. But I have a formula for U. So this is the inner product of V minus inner product of V W divided by norm W squared W, and then inner product of W. And that, so because the inner product is linear in the first entry, I can write that as the inner product of V with W minus, and then I'm going to pull out this scalar. So I get inner product of V and W times the norm of W squared divided by norm of W squared times the inner product of W with W. Okay, but now this cancels with this, and I end up with inner product V minus W, V with W minus the inner product of V with W. So I get 0, and that's what we wanted. Okay, so this is one of the reasons why inner product spaces are really useful. If you want to find the projection of one vector onto another, or really onto the line spanned by another, then the coefficient is given easily in terms of the inner products. Notice I could also write this as the inner product of V with W divided by the inner product of W with W. Okay, let's stop there for today, and we'll pick it up from there next time.